Hello friends, you are welcome to the GMAT 41's YouTube channel. In this video lesson, I'll be teaching you how to solve a problem which is fluid mechanics related. You see, when you are required to determine the dynamic viscosity or simply the viscosity of fluid, usually we rely on Newton's law of fluid, which states that the shear stress in the fluid is directly proportional to the shear strain. There, the constant of proportionality is known as the viscosity of the fluid. Now, in this question that I have here on the board, we are given the area of the plate to be 0.6 square meter, and that plate is placed on a plane, an inclined plane. That plane is inclined at an angle of 30 degrees to the horizontal, and the plate is moving on the plane with a velocity of 0.36 meter per second. Now it is said that between the plate and the plane there is a cushion of fluid which is 1.8 millimeter thick. Determine the viscosity of the fluid. Okay, if the weight of the plate is 280 Newton. And then of course in the second part of the question we are required to determine another type of viscosity, which is the kinematic viscosity, given that the specific gravity of this fluid under consideration is 0.85. Alright, since this is an inclined plane problem, we commit no crime sketching something about inclined plane, even if it may not be absolutely necessary in solving this question. But just for you to get an idea of what the question is all about, I'd like to do this. So let us take this as the inclined plane. The angle is 30 degrees. Now, let the plate, which is placed on the plane, be this. Is that okay? And the area of the plate is 0.6 square meter. We were told that there is a cushion of fluid between this plate and this plane. I will use this blue marker to just draw a line like this to represent that cushion of fluid. You know, the fluid will not allow the plate to make direct contact with the plane. So it's like the plate is floating. Are you following, right? On the cushion of fluid. Thereby making it a bit slippery, you know. It's just like when you try to move a plate on top of water. Just go straight on. So that's the idea. Alright, the velocity was given to us in a question, and then that's the basic thing. The weight of the plates. The weight of the plate was given to us. So this is the weight of the plate. Comes this way, W. And of course, you know, it was given to us to be 280 Newton. Do not forget that the weight of something is equal to mass times acceleration due to gravity. Alright, because it's possible for this weight given to us to be mass in the unit gram. You would have to convert it to Newton, representing its weight. Alright, we know that there are two perpendicular, components of this weight. So there is something, a line that will come this way. That line is perpendicular to this. Alright, it's perpendicular to the plane. And this, of course, is just another component of the weight. Now, this weight is between this and this perpendicular line. Just like having something like this, right? And then you have the weight this way. So this is at 90 degrees. So this weight can be resolved in this direction. I'm going to use F, permit me please, because the force that is pushing this plate down is generally given as this force is acting parallel to the plane, which is this. So this angle is 30 degrees. Take note please. From here, it's kind of corresponding angle to this part. So here is 30 degrees. Fine. So we shall resolve these weights in the direction of this force. And from our dynamics knowledge in physics, that F is equal to mg sine theta, which is still the same as W sine theta. If I do that, this part I can quickly get it to be 280 times sine 30. Alright, and then the force that is pushing that plate down, acting parallel to the plane, is 140 Newton. Sine 30 is 0.5 times 280 is half of 280, which is 140 Newton. Alright, so we have gotten the force. We need this force in this calculation because from Newton's law of fluid, shear stress, which is force over area, is equal to mu. That mu is dynamic viscosity times du dy, where du is the velocity, dy is the fluid thickness. So du dy, we call it the shear strain or the velocity gradient. Okay, let us move on. Knowing that the formula will contain our force area, all right, and then du dy. We know u already. The velocity is given from the question. Let's say du 0.36 meter per second, and of course the thickness dy is 1.8 millimeter. Can convert it to meter, multiply by 10 raised to the power minus 3, or simply 1.8 divided by 1000. All right, so from Newton's law of fluid, shear stress is equal to dynamic viscosity times the velocity gradient. Shear stress equal to this, then du dy. This is our viscosity, this Greek symbol. Good. Now this shear stress is force over area. Because of the data given to us in this question, we need to break it down to force over area. We know the force pushing the plates down the plane. And of course, we know the area of the plate, 0.6. That's going to be equal to the viscosity, then times velocity divided by thickness. If I substitute my values here, the force is 140 divided by the area, which is 0.6. And then this is equal to the dynamic viscosity, I don't know. That's what I'm looking for in the first part of the question. And now I'm multiplying it by the velocity gradient. The velocity is 0.36. And then I'm going to divide it by the thickness. The thickness is 1.8 times 10 to the power of minus 3. Now I'm going to work this thing out once and make the viscosity subject of the formula. To do this, I'll cross multiply first. Then if you cross multiply, 140 will multiply this term. And then 0.6 will multiply the viscosity and 0.36. So that making viscosity subject to the formula, it's not going to be 140 times 1.8 times 10 to the power of minus 3. I'll be dividing it by 0.6 times 0.36. Okay, at this point, we need to reach out for our calculator and then calculate the value of the dynamic viscosity. So I'll be getting my calculator right away. I hope you've gotten yours too, right? So let us do this together. So this is 140, and then I'm multiplying it by 1.8. You know, whenever I'm calculating something with all these powers of 10, I like using indices a lot. So with this thing carrying 10 raised to power minus 3, I would like to bring it down. If 10 raised to power minus 3 comes down, it will become 10 raised to power positive 3. Just like if it was to go up, it will become minus 3 as power. So I'm just pressing 140 times 1.8, then I will divide it by open bracket, because I want to press everything together in the denominator. 0.6 times 0.36 times, remember I said that the 10 raised to power minus 3 is coming down to the denominator to become positive 3. And 10 raised to power 3 would give you 1000. So 0.6 times 0.36 times 1000. See, I'm kind of very careful sometimes if I'm pressing my calculator. That's why a good knowledge of mathematics is good. Is that okay? To guide you. Because some calculator, if you press this thing once, although mine is a bit powerful, Casio, but some calculator, if you dare to press this thing once, the interpretation will not be funny. Alright, so from what I have here, this gave me 1.1666666. I can approximate to 1.17. And the unit of viscosity is Newton second per square meter. Good. We are done with this. We shall proceed to the second part of the question. In the second part of the question, we are asked to get the kinematic viscosity. And we use the symbol this, pronounced nu. Is a Greek letter anyway. That's not what we are studying. So kinematic viscosity, we don't know. Good enough, there is a relationship between kinematic viscosity, dynamic viscosity, and the density of the fluid. So we have that the kinematic viscosity is equal to dynamic viscosity divided by density of the fluid. Now our problem is to get the density of the fluid, because in the question we're not given the density of the fluid. But look at what was given to us, the specific gravity of the fluid. And the specific gravity is the same as relative density, which relates the density of any liquid to that of water. The density of water is 1000. Actually, the formula is specific gravity of any fluid, so SGF, subscript F, equal to the density of that fluid divided by the density of water. And the density of water is 1000, like I said. So if you cross multiply, you're going to get the density of the fluid to be 1000 times the specific gravity given, which is 0.8. So we're going to do that here. Is that okay? This means that the kinematic viscosity is equal to dynamic viscosity is 1.17. So divided by, this is going to be specific gravity, which is 0.85, multiplied by density of water, which is 1000. In conclusion, we can reach out for a calculator and press that. 1.17, we are dividing it by 0.85 times 1000 is 850, right? Good. So divided by 850. Alright, and this is what it gave to me. 1.38 approximately times 10 to the power of minus 3. Okay, that's the same as 0.00138. So we are done with this. The units of kinematic viscosity. What's the unit? Let's see. Meters squared per second. That's the unit of kinematic viscosity. And this is how we analyze this problem. I hope you learned something from it. If you do, even if you do not offer fluid mechanics, it doesn't matter. You can still just click like and of course the subscription button. Subscribe to my channel, GMAT41. You can share my videos, tell your friends about the GMAT41's YouTube channel. Tell your friends to tell their friends who know another friend, okay? We have so much to offer you from this channel. Alright. You may also wish to join my tutorial classes for full range of learning of courses and subjects related to what you study. It's alright, I'll be seeing you in our next class where I will drop a video lesson teaching you how you can solve related question as this, but this time around using the concept of differentiation. Because of course, from this Newton's law of fluid, this shear strain, also known as velocity gradient du dy, you can say that it contains a differential coefficient. So we can use the knowledge of differentiation depending on some kind of question given to us, especially if the velocity profile of the fluid flow is given. You can use differentiation knowledge to deal with that. You would not want to miss that video, right? So click the subscription button and personalize your subscription so that once I upload a video lesson, you will be notified.